Now, when you want to do sequence to sequence, which we will see a lot in our transformer models, we do this encoder decoder business. So you encode your input sequence into a single vector. You start with your x1, you feed it into your model, you have your h0. Based on your x0, this and the weights, so the weights, remember, here are 2, your wxh and your whh, you get your h1. Then using this and your x2, you get your h2. Then using your this and x3, you get your h3, all the way to your ht until your sequence is finished. So this is now in some sense an encoding of your entire vector, your entire sequence, right? And this is in some sense that thought vector that I was talking about. So you have encoded your entire sequence into this one vector, and this is a disadvantage, and we talk about this later. So you have your input sequence, and this input sequence can be represented. So this is, let's say, your embedding of this input sequence into this one hidden vector. And then we give this hidden vector into our decoder, and for the decoder we have a different set of weights, but the operations are exactly the same. But the only thing that is different is that at every hidden state we also have our output. We have our y1, y2 and all the way to yt. So you have a one to many mapping, and here a many to one mapping, right? You have this many, but you have no output. You just have your hidden state, and then this hidden state goes into a different model, but then it's trained end to end, because losses only come from here, and then these losses go into here, right? And this is when we update the weights of the encoder, and these are the weights. So this is why I call it W2, and this is why I call it W1. Now let us kind of concretize what we have learned. So what we have learned is very simple. The model comes with these hidden states, right? So this hidden state is a state of the machine learning model. Also, the weights that it comes with is the state of this machine learning model. Now, based on the input, we update the hidden states. Also at runtime, we update these hidden states, and we don't update the weights obviously when we are kind of doing the inference at runtime. We only update the weights during the training time, like any model. And with this hidden state, we kind of keep updating this hidden state based on the new sequence, let's say the new word that comes in, and using the weights. And then finally we can either choose to kind of use this hidden vector at different time step to generate the output that we're interested in, the y's that we're interested in. So let's concretize it. Let's say we have our vocabulary, right? So we will never do this in practice, but let's say our vocabulary are only these 4 letters H, E, L, O, and we have this training sequence, hello. So we have these letters H, E, L, L, O. First, so this is X1, X2, X3, X4 and X5. So this is what we want our model to learn. This is our training data. So how do we represent this training data? We can represent H as this one hot vector within this vocabulary, right? So our H will look like this 1 and zeros everywhere else. What will our E look like? It will look like our 0 and then 1 and 0, 0 and so on. And this is what we've written here, right? So your H looks like this, your E looks like this and so on. It's basically one hot encoding on your vocabulary. Next, we have our hidden layers, right? So we want to then update our weights of X and this based on this, right? So you have your, input coming in, you have already, so this is your H0, this is your X1, this is your H1, this is your x2 and so on, and we use this function to then finally, so where is your your hidden, so this matrix goes from your hidden to hidden, and your this matrix goes from your input to hidden. And finally what we want are these target vectors, right? So this is the output, but then our target are essentially those one hot vectors, right? So this is what we got as output after multiplying these hiddens with your W H Y. So W H Y. So you multiplied your W H Y with this and you got your output this. And what is your ground truth? So your ground truth here obviously is, you know, 1. So whatever is the input is the same thing is what we want as output, because we want it to learn hello, or you can also train it to learn the next and so on. But here, so here we want to train it to learn the next letter, because what we want it to do is, if we start it off with, let's say, H, we want it to predict E, and then we will take that E and put it back, and then we will want it to predict L, and then we will take that L and put it back, and we would want it to predict the next L. So our ground truth here will look like this, right? So it will look like this one hot vector where we have a 1 here and 0 everywhere else. And then we will create some kind of a loss between these two, right? So we will maybe have a cross entropy loss between them. So this is how we will train the model. So again, how will we train it? We have these hidden vectors, we have our inputs, we know how to create these outputs. On the output we will have a loss, and then we will take all these losses, we will then backpropagate through all of them. Yeah, so this is how the training works. And at test time, what we will do, we will sample one character at a time. We will kind of give our model this, we will have the hidden layer from some initialization or from something that we have learned. We will again look at the details later in our assignment, and finally we will get this final output. And on the final output we will kind of do a softmax, and then on the softmax we will do the loss. So previously we didn't mention the softmax, but we do a softmax so that we can then do cross entropy, and we will then sample from here. Sample meaning you will sample from this distribution. You will not always take the, you know, the output with the maximum probability, because you want it to kind of be generative, because you want it to kind of give different outputs at different times. And this is one of the reasons why our modern LLMs are not deterministic, right? So you will sample from there, and then let's say we were able to sample E, and this E is what we are going to put back into the next step of our model at runtime, right? And then what happens in the next step, we kind of do the same thing. We take this, we multiply with your H, and then we already have your this, then whatever are the output vectors, we do a pointwise sum, we put a tan H on top of this, and that gives us, you know, the next one here. And then to get the output, we do your W, you multiply it with your HY, and then that gives us the output. We do the softmax, we get the distribution. From this distribution we sample, let's say we get L, we put this L in to the next one, and so on, and we keep doing that. This is so we call it autoregressive models, right? Why autoregressive? Because it regresses itself, it regresses the same thing. So we have these sequences available, and we want to predict, let's say, the next letter, the next word, the next sentence, you know, the next frame in the video. And this is why these are autoregressive. And because of this autoregressive nature, this is also self-supervised, because we don't really need labels, because we just need data. The data happens to be in a sequence, so we don't need labels, because we try to predict the same thing, and based on that we can do some powerful things, right? So, and then at what we do is we do this backpropagation through time. We get all these different losses. Remember, we then combine those losses, we add all those losses up, and then we backpropagate it, and we forward propagate through the entire sequence and backpropagate through the entire sequence to compute the gradient. And we do it in chunks. What if our sequence is very, very large, right? So we would do it in chunks. We would break it in chunks, and we would backpropagate through it, and we would update our weights. We would backpropagate, you know, we will collect the loss of all of that, we'll backpropagate and update the weights, and so on. So this is, and that what I just explained is called truncated backpropagation. So run backward and forward through chunks of the whole sequence instead of the whole sequence. Because what if your whole sequence is like a full book or the entire internet? You cannot kind of do a backprop over all of that. So you chunk it. You chunk it to some manageable size that your compute and memory can handle. And we carry the hidden states forward in time forever, but only backpropagate through some of the normal states, right? So obviously we have the hidden states and we keep kind of taking that hidden state forward, but when doing forward we only do this much, and then we create the hidden state and then we do our business within this much. Similarly, we take it through this much, we do our business through this much, we compute the loss, we then backpropagate through this much, then here we compute the loss and then we backpropagate through this much. So this is called truncated backpropagation through time.